Welcome to Pomodoro Joe for Saturday, June 10th, 2023. Today we're doing LeetCode problem 1802, maximum value at a given index in a bounded array. This is a medium problem. You're given three positive integers, n, index, and max sum. You want to construct an array nums, which is zero indexed, that satisfies the following conditions. The length of nums is equal to n. All right, so we have exactly n elements. Nums at index I is a positive integer where 0 is less than or equal to I, which is less than n. Okay, so for every element in our array, we have to have a positive integer, so it has to be at least 1. All right, the absolute value of nums index I minus nums at index I plus 1 is less than or equal to 1, where 0 is less than I, which is less than n minus 1. So this is just saying that every element can only be at most 1 away from the previous element. So it can be the same, or it can be 1 plus 1 or minus 1, but it can't be anything greater than that. All right, the sum of all the elements of nums does not exceed max sum. All right, so the sum of our entire array can't exceed max sum, and nums at index is maximized. Okay, so we have a peak where we maximize our value at nums index. Return the nums index of the constructed array. Note that absolute value is equal to blah, blah, blah. Okay, so, wow, this is a tricky one to understand, but here are the basics. Number one, we have to construct an array, but we don't actually have to construct the array. We just have to conceptually construct the array. But we're tasked with creating an array of exactly n elements in length. We want to maximize our value at the index, but in order to do so, we have certain constraints. Every element in the index has to be a positive integer, so it has to be at least 1. Every element in our array has to be equal value or 1 plus or minus the previous element, but it can't be anything greater than that. You can't have a delta greater than 1. All right, so this is a tricky problem. We'll put 25 minutes on the Pomodoro timer and we will get started. Okay, so for this one, I think I'm going to do an exhaustive search or a bounded search. They call it a bounded array, so I'll call it a bounded search. Now, a bounded search is basically we can find a lower bound and an upper bound for our value at index. Then we can just search every value in between, finding the maximum one that satisfies the conditions that are laid out right here. So let's see, what pieces will we need? Well, we'll need some min value to start with. I'll just set it to none at the beginning, and we'll need a max value to start with. So we'll go between the min and the max value. Let's see, we'll need some result at the end. And we'll return our result. Let's see, this has to be at least 1. So we have a min value and a max value. Let's see, we'll also create some function checking whether or not our value is valid. We'll just call it isValid. Take some value x, and for now we'll just pass. And then we just have to go for every element, so we can just say for I in range from the min value to the max value plus 1, because we want it to be included. We'll just call, let's see, if is value, is not value, is valid. Is valid, and we'll pass in this I. Then we'll just continue. It's only when we're not valued, then, okay, if it's not valid, then we can return I minus 1. How about that? But then let's see. We could go from the max value to the min value with a step of -1. And as soon as we find one that doesn't work, no, as soon as we find one that does work, there we go. So we'll go from the max value to the min value -1 at a step of -1. And if we find a valid answer, we can just return that answer. Otherwise, if we get to the end, we can return our min value here. Hopefully this will have actually returned in here, but just in case. All right, now I have to create this is valid. Okay, how do we figure out if this value is valid? All right, well, let's take a look at our array here. We know it has to have at least ones. So I have a bunch of ones. Let's just choose 5 to start with here. Let's say we're allowed to have, or we're looking for a maximum value at index 2. So that's 0, 1, 2. So we can make this 2, and that'll fall off to 1 and 1. But if we make this 3, then this delta is too great, so we have to make these 2, and then 1, and so on and so forth. And then this, if we made this 4, this could be 3, but then this would have to be a 2. So it kind of depends on our max sum here. So we could have some value. We don't necessarily have to go down to 1. It really depends on our max sum. So what is our min value? Well, let's see. Our min value would be if we just divided our max sum up among every single one of our elements. So that should be pretty easy. So that's max sum. I'll do an integer divide by the number of elements we have, n. That's our min value. Now what's our maximum value? Well, let's see. If we have our min value, so that's just leveling off this playing field, right? So let's say these are all 5s. 1, 2, 3, 4, 5. So that's leveling off our playing field. Now if we pop this one up to 6, this one could be 5, and this one could be 4. So then we could pop this one up to 7, and this could be 6, and this could be 5. So it looks like it depends on how far away we can get from our index. So the minimum value would have to be the one, or sorry, the maximum value will have to be the minimum value way out here at the edge plus n divided by 2. Well, and it's not necessarily divided by 2, it's divided by 2 in this case because we happen to be in the center. But if we were way at one edge, we could have basically slope down by n elements. So at most we could have max sum, or sorry, our max value would be our min value plus n, I think. Okay, so our min value could actually be smaller though. That's interesting. There's probably a better max value here. I bet we could find a better max value, but I think this is our maximum value. So we'll start with this. All right, back to is valid. Okay, so in our array here, we kind of have 5 zones. So we have our index in the center, or index on one, well, I'll call it the center. It doesn't have to be the center of the array, but it's the center of our zones. So we have the index. Then in order to maximize our index, we need to minimize all of the other values because we have to stay within this max sum. So in order to maximize our index, we make it the max, we minimize the other values, which means starting from the max at our index, we will slope down at a rate of 1 per element. So this is like our slope. We'll be decreasing our values on either side of our peak here. So zone 1 is our index, it's the peak. Then we have zones 2, which are sloping down on either side to the left and to the right because we're trying to minimize those values. Then we have our final area where, let's see, we might reach the end of our array. So we stop or we end, or we flatten out because this could end up hitting 0. And if we hit 0, we can't really have 0 values for our elements. We have to go to 1s. So we'll go flatten out. And that will go to the end, and we'll have that on both sides. So this will either be the end or flat. So these are like our 5 zones. The peak at our index, we slope down on either side, and then we either hit the end of our array or we hit a flat where we basically just have 1s until the end of the array. That's a lot to keep track of. All right, so let's just do this. Okay, so we need to figure out if all of these values summed up is less than our max sum or less than or equal to our max sum. So we'll have some value here. And it will start as x because we have at least x at our peak here. Then we need to add to that a certain amount on either side, our slope here. Oh boy, so what do we add to this? Well, we need to essentially create we need to know how many elements we can go to the left and to the right. So how many elements are in this slope, and then how many elements are in the flat if we have a flat. Okay, so I'll have this like slope left, slope right, and flat left and flat right. All right, let's do that. So let's figure out how many elements are in our slopes. So our slope left. Actually, we should start with flat left. Well, oh, this is going to change depending on our input. So the slope left and the flat left will change depending on our peak. If we have a high peak, then we might not have any flat. If we have a low peak, we might have a long flat with a little bit of slope. So I can't really have a slope left, but I could have the number of elements to the left and to the right. There we go. So I'll have left elements, or element count. I'll call it left count. So this is how many elements are to the left of our index. So that means this is just index. All right, and then our right count. How many elements are to the right of our index? Well, that should be our total, n minus 1, because we're taking away our index itself, and then minus the left count. That makes it easy. So our min value, our max value, our left count, and our right count. Cool. Now we still have to figure out our left slope and our right slope. Now these are going to vary depending on this value x. All right, how do we figure those out? Well, let's start with our left slope. We'll just do the left slope count. I believe that's going to be the count that we can have here. So we can have x minus 1 in our slope, and that should be the same for the right. Okay. Oh, but that is going to be our index. So this is going to be our index plus x minus 1, as long as it's less than n. Otherwise, it'll be n. Oh, this gets really tricky. So we have to figure out whether or not we're going to hit our end. And this is the same thing here. We can have x minus 1, but it's going to be the index minus x minus 1. So I'm not being very clear with this, am I? So we're looking at our index. How far to the left can we go with our slope? So at our index, we have value x. At the index before our index, so at index minus 1, we can have x minus 1. That's our value. And we can have x minus 2, x minus 3 as we move back to the left. We're decreasing our values at those elements. So as we're moving to the left, we can move at most x spaces or x minus 1 elements before we hit 0. Now at 0, we can't actually have a 0 element, so we stop at x minus 1. So as soon as we reach x minus 1, all the elements before that will be value 1. So we look at our index, we can go at most x minus 1 elements to our left before we flatten out. So this is index minus x minus 1. So this will be the index at which we have to flatten out. But our x could be, let's say, 10. Let's say we choose some large value, 10. But our index could be 2. Well, we're going to hit the beginning of our array before we ever flatten out. So we actually have to do a minimum of this or 0. And same thing with our right slope. We have to do a maximum, a minimum. Again, a minimum because we could exceed the bounds. we'll do index plus x minus 1 because we're going from the index to the end, or n minus 1, whichever one is smaller. Okay, so that's going to give us our left and our right, and this shouldn't actually be count, this should be index. All right, so that's our left slope index and our right slope index, and then our flat, let's see, left flat. This will actually be a count. So that's going to be essentially just our left slope index. So, not left slope. So this is going to be essentially, we'll have a bunch of ones, 1, 1, 1, 1, until we start sloping up, 2, 3, 4, 5. So whatever this index is, so this is 0, 1, 2, 3. Looks like it's going to be index plus 1. Let's say a right flat count. And this will actually be n minus 1. So we have to start at the very end, and we'll subtract our right slope index. I'm going to speed through a bunch of this right now. This is just finding the boundaries of these different areas. It's not super interesting. You can check out my code in GitHub, or you can jump to the end where I go through it a little bit better later on. All right, here back to the program. So now we actually have to figure out how these help us in terms of calculating the value at these elements, or the sum of the values at these elements. So we'll have sum of elements, and we'll need to start with some x. So we need to know the start value, and we need to know how many there are. So count. Okay. So we start at x, and we have count number of elements, and every time we go through, we have to remove one from our x. So our value will start as, I guess, 0. Okay. So we'll go count. And so let's see, we will say val plus equals x minus ri. So we'll take away 1, or we'll start with taking away 0, then we'll take away 1, then we'll take away 2, 3, 4, and that gives us our slope. All right. And we will cache this because I'm pretty sure we'll be doing the same values over and over again. So we start our value at x, then on the left and the right, we'll actually go down to x minus 1. So let's see, we'll actually have to calculate our value. We'll add our left slope, so we'll add the sum elements. So this will be x minus 1, and we'll have a left slope count. I'll have to create that, and then the val plus equals the sum elements, starting at x minus 1 again, and then be the right slope count. And then we need to add our flats, basically. So the left flat count could be 0. Okay, this is also where we need to do some checking on our bounds, because those might be 0. And then the val plus equals our left flat count. Again, those are the number of elements, but they'll all be equal to 1, so we'll be adding that as just straight up value here. And then at the end, we will return whether or not our value is less than or equal to our max sum. Wow, that is a lot of work. And I still haven't done this left slope count yet. All right, so the left slope count, well, we've figured out the index. I think that'll just be our index minus our left slope index. I'll have to double check this. And this one will be the right slope index. Minus our index. I have very low confidence in this, and we have 1 minute left. Let's just see how this goes. Oh, that does work. Okay, we'll submit this and see how we do. I'd be surprised if we pass, but let's check it out. We have a wrong answer, so we'll use this test case. Let's see. I was pretty sure at this point that I had something wrong with my boundaries calculations. This for the slopes and the flats. I think I was off by one somewhere. So I actually had to revert to going to pencil and paper, drawing out some diagrams. Unfortunately, I don't really have software here to show that to you, so I went offline. I stopped the video, did my diagrams, came back, and then I corrected the errors in my calculations. And we'll jump back in here. And we're back. Sorry, I had to take a break and do a little bit of investigation here. So after some investigation, turns out finding these indices can be really tricky. So I'll show you what I ended up doing. And I'm just going to fast forward through this to spare you some of the trial and error here. So the first thing, this was wrong. I don't want the minimum of the index or 0, because this can result in negative values. I really want the maximum of this or 0. The other thing that I had wrong here, I'll just jump ahead. So that's one thing I had wrong. Another thing down here, this should be from n minus 1 because we want to go from the last index. Okay, so this does seem to work, at least for the test cases. So let's try this. All right, so that works for the test cases. Again, finding these indices was kind of tricky, so that's why I had this print here. All right, let's submit this. I don't think this is going to run in the time that we need, but it's worth a shot. Yep, time limit exceeded. We only get 127 out of the 370 test cases. Wow. Okay, so we'll add this test case to our list here, and we'll try it, but we're going to have to do a couple different things for this one. I mean, we're only beating a third of the test cases. Oh, that's interesting. It shows us beating this test case now. All right, well, first I'll get rid of this because we don't need this anymore. Next, instead of going through every single value, let's do a binary search. And binary searches are fairly straightforward, but let's just get rid of this. So now we'll have a low and a high. So the low index will start at 0, and the high index, actually it's not going to be an index, is it? It's going to be the value that we're searching for. So this will be the min value, and the high will be the max value. Now while our low value is less than our high value, well then we'll find the mid value. What's the midpoint? Well, that will be the low value plus the delta between the high value and the low value divided by 2. So this will be high minus low, and we will do an integer divided by 2. So this will basically find the midpoint between high and low by finding the difference between the two, finding the middle point of that distance, and then adding on the low so we get the base. Now that we've found our midpoint, we check if it's valid. So if is valid, the midpoint, if this is a valid midpoint, then we can raise our low to the mid plus 1. If it's not a valid midpoint, then we need to lower our high down to the midpoint. Okay, so that works. So now we have our basic binary search, searching between our low and our high, which is our starting min value and our starting max value. Let's just see if we can pass. Time limit exceeded, but we do a little bit better, 212 out of the 370 test cases, so we'll add this test case to our list here. All right, now we need to get into some more mathematical things. So at this point, we have our binary search. We're just checking values between the low and the high, doing a binary search pattern. Now our is valid is slow. We're basically doing a lot of calculations in this is valid. This is where I had to actually do a little bit of looking up because it's been a while since I've done this type of math. But what you can use instead of doing this type of iterative approach to summing up all these values, you can use a mathematical approach. Now this is an arithmetic sequence, so there's something called an arithmetic sum. And let's see if I had to look this up, so I'll try to leave a link in the description. Let's see if I can remember how this goes. In fact, I am just going to copy and paste it. All right. So the arithmetic sequence formula goes like this. The sum of the sequence will be the element at index 1 at the start of the sequence plus the element at the index at the end of the sequence, and that whole thing will be multiplied by the length of the sequence divided by 2. And note that this is a floating point divided by 2. So this will give us the sum. So instead of having to do this sum, we can actually do this sum, which should be a lot faster. Now, in this case, we actually need the element values at index 1 and index n, which is a little bit different than what we have, where we have the end value and the count. So some of this will be the same. This end value will be the same, but the start value might be a little bit different. So we need to change some of this. Actually, do we need to? No. We can actually calculate our start value from these two elements. Let's see if we can do this. I'm not sure this is going to work, but let's give it a shot. Let's see, this will be our x minus our count, or 1, whichever is bigger. So we either start at 1 or we start at x minus the count. I think it might be x minus count plus 1. And the end value will be x. And now we do our sum here. So we'll return, let's see, this will be start value plus the end value times our count divided by 2. All right, so that should give us this value. Nothing else needs to change in here. Let's see if this still works. Oh, that works, and we're passing this test case. All right, let's submit that, see how we do. And we pass. I'm actually a little bit shocked by that. All right, and we do okay. We beat 33% for runtime and 53% for memory. Not too bad. Not great. Clearly, there's a lot of room for improvement here. But there's still a lot. This is pretty messy, so you could probably go through and clean a bunch of this up. Unfortunately, I am really low on time. I'm probably not even going to have time to edit this and get it posted today. So apologies if you're seeing this late, but it's a tough problem. This is actually a pretty tricky medium, mostly because I didn't remember my arithmetic sequence formula. So I did have to look that up. All right, so for this one, we're using the exhaustive but bounded search pattern. So we basically find our min and max values that we know we have to be somewhere in between. Then we'll do a binary search between those min and max values using, in this case, an arithmetic sum to try to figure out the sum of all the elements in our array. So this one's super tricky for a medium problem. Not as tricky as new 21 game, but still pretty tricky. Okay, that is it from me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.